Hey, what's up, what's up, what's up? All right, this is the last PowerPoint for Chapter 15. Once we finish this, we will have a day to review, and then we will have an exam just over Chapter 15. Chapter 15, hopefully you know by now, is about equilibrium. The first PowerPoint we talked about the writing KEQ equations. The next one we talked about solving KEQ equations. And the one we just did yesterday was all about finding different, using the reaction quotient to find which way the reaction will proceed. Our PowerPoint today is dealing with what is called Le Chatelier's principle. So if we can get it started here, we'll what's going on. Uh, and this is obviously a French individual. And what we're going to see today is basically what this table here is showing us is that at equilibrium, the percent of ammonia at equilibrium is higher when the pressure is greater, and also we can see when the temperature is lower, and we'll see why that happens. And the reason that does happen is because of Le Chatelier's principle. Okay, our objectives for today, we're going to talk about how an equilibrium is shifted by stresses in a reaction. We're going to talk about how temperature changes affect KEQ, and we're going to talk about catalysts. Okay, so Le Chatelier's principle. Again, that's not a spelling test. You will not have to spell that on the exam. Certainly, you will see more multiple choice questions than free response questions regarding this. But basically, it states that when you're at equilibrium, if the temperature changes, or if one of the pressures changes, or one of the concentrations changes, the reaction will shift, and that is a key word there, is that it will shift um, to counteract the effect of that disturbance. Okay? So, the four types of disturbances, or the four types of changes that might occur in a reaction, one of them is you might take some of the reactant or some of the product, and you might add some more of it, or you might take some of it out. That will cause the reaction to shift. Okay? The second one is you might find a change in the pressure. If the pressure changes, that's going to affect the reaction, and it's going to cause a shift. If the temperature changes, again, temperature changes might affect it differently, whether it's exothermic or endothermic. And then we're also going to talk about what happens to a reaction if you add a catalyst. Will it cause a shift to occur or not? So the first one, if you add or remove a reactant or a product. So we've got one of the chemicals that's involved in the reaction. And let's say you take some away or you add some, the equilibrium is going to shift until you've got a new state of balance. So, chemical system at equilibrium, we're going to add a substance. So we're going to add, um, let's say if we come up here, here's our reaction. So again, we've got nitrogen react with hydrogen, make it ammonia. So the reaction, and we're going to add a substance. So let's say we're going to add, let's add some nitrogen. Okay. The reaction is going to shift to reestablish equilibrium by consuming part of the added substance. So if we add more nitrogen, the reaction is going to proceed in a way to use up some of that nitrogen we've used. Well, the only way the reaction can use up some of that nitrogen is to shift it to the right to produce more ammonia. So, if you add more of a substance, the reaction is going to shift to, and it's going to use up that substance that you've added, shifting it in the opposite direction. It's going to move in a direction that forms more of that substance. Okay? If you remove a substance, so if you take some N2 out of this reaction, so the N2 is gone, the reaction is going to shift in the other direction to make more of that substance. So if you add nitrogen, the reaction is going to shift to the right to use up the nitrogen that you've used. If you take away some nitrogen, the reaction is going to shift to the left, and it's going to make, in an attempt to make more. Okay, same thing with the products. If we add more, if we throw some more ammonia into the container, the reaction is going to shift to the left to use up that ammonia that we've added. If we take some of that ammonia away, the reaction is going to want to make more of that, so it's going to shift to the right to balance that out. Okay? So when we add a substance, it's going to consume it by shifting it in the opposite direction. If we remove a substance, it's going to want to form more of that substance, shifting the reaction in that direction. Okay, so here it says more hydrogen were added, so we're going to add some more hydrogen, so that's going to go up. The reaction is going to want to use that additional hydrogen, so it's going to shift the reaction to the right. Okay, so yes, the nitrogen will also go down, but the ammonia will go up. Now, does that affect the actual value of KQ? And the answer to that is no. Because what we see is that, look, right at this point right here where you can see the hydrogen was added. So yes, once it's added, it's going to use some of that up. So we can see that the pressure of hydrogen is going down. The same time, the other reactant, nitrogen, is also going down. So nitrogen and hydrogen are both going down. Well, if we think of the KEQ equation, those are on the bottom, okay, because they're reactants. NH3 is going to be on top. It's a product. Well, you would naturally think then, well, then KEQ has to change, because if the product goes up and the reactants both go down, then KEQ has to change, which is very close, which is actually correct. However, because hydrogen jumped up so much, because here, remember, it's at equilibrium. It's now at a new equilibrium. Notice that hydrogen, even though it went down from what it jumped up to, is still much higher than what it used to be. It used to be right here, and now it's all the way up here. Nitrogen is a little bit lower, but hydrogen is actually higher than where it started with. So the reaction, so KEQ actually stays the same. Even though the reaction has shifted in one direction, the value of KEQ has not changed. Okay, if we remove some ammonia from this reaction vessel, how would the reaction shift? Well, initially we would see, just like here, we would see a drop in the value, but then it would want to make more. So what we would see is that it would slowly climb back up to reestablish equilibrium. So the ammonia value would go up, the hydrogen values and the nitrogen values would both go down, and so we would find that that reaction would shift to the right. So if you're in a business and you're trying to produce ammonia to make money, certainly as you remove ammonia from your system, you're going to find that it's going to want to make more and more ammonia. Because this is an equilibrium reaction, that if all you're trying to do is produce ammonia, well, even under ideal conditions, you're still going to have some nitrogen and hydrogen in there. When all you're really trying to make is ammonia, so you can sell it, you're still going to have some nitrogen and hydrogen. So you want to force this reaction to go forward as much as you possibly can to make as much of the product as possible. There we go. Now, the pressure. Say we have a gas reaction such as this same one here. When you change the pressure, there's different ways you can change the pressure. One way you can change the pressure is you can put more of the reactants or the products in there, or you can take some out. If you add more reactants or products, it's going to increase the pressure. Well, we already talked about back here what happens when you do that. If you change the pressure simply by changing the size of the container, so in this case, if you make the volume smaller, okay, so the volume is decreased, when you do that, we know that the pressure increases. The pressure increases, and so there's more collisions per second. More collisions with the outside of the container, so obviously the pressure is going up. The system's going to respond by shifting the equilibrium, and there's the important part here. Let's see if we can do something here. Let's go. Should we do yellow? Yeah, let's do yellow. The system will respond by shifting the equilibrium to reduce the pressure. And the way that you reduce the pressure is you reduce the total number of gas molecules. Okay, so again, let's go back to here. So let's compare this side to this side. On this side, how many total moles of gas molecules do we have? Well, we've got one nitrogen and we've got three hydrogens. So on our left side, we have four gas molecules. On the right side, we have two NH3s and that's it. So we have two gas molecules. So when you increase the pressure by decreasing the volume, the reaction is going to want to shift to the side that produces less gas molecules. This side has four, this side has two, therefore the reaction is going to shift to the right and it's going to produce fewer gas molecules. Conversely, if you were to increase the volume by making the container bigger, then the opposite would occur. Now it's got more room to move around. The reaction is going to want to proceed in a direction that produces more gas molecules. So the reaction would proceed to the left because we've got four gas molecules here, only two gas molecules here. Well, let's say we had a reaction where we had four gas molecules on one side and four gas molecules on the other side, not two. Then any change in pressure is not going to cause a shift in the reaction because both sides have the exact same number of gas molecules. Now, if you have a solid, let's say this isn't a gas and this is a solid, well, then that doesn't count. Then you would only have three gas molecules on this side. Okay, so it's only gas molecules that are affected by pressure. So if you have aqueous or solids or liquids, none of those count when you're counting the gaseous molecules. Okay, so reducing the volume causes an increase in pressure, and it's going to shift in the direction that reduces the number of moles of gas. When you increase the volume, so you're making it bigger, it's going to shift in the direction that produces more gas molecules. Okay, now if all they say is the pressure is increased and they don't tell you how, then you cannot assume that the volume has increased or decreased, because there's many different ways you can change the pressure. If they just using a lot of ambiguity, say that the pressure is changed and they don't specifically say how the pressure is changed, then you cannot make an assumption about, oh, well, the pressure is increased, so the volume must have gotten smaller. You cannot make that assumption. So when they say the pressure has changed without specifically saying how, then you would have to say that there's not enough data to answer the question, or there's just no shift at all in the reaction. Okay, so in this reaction here, notice we've got one gas molecule, we've got one N2O4, we've got two NO2s. So if this volume is decreased, then the pressure is certainly going to increase. When the pressure is increased, it's going to want to make less gas molecules all total. So the reaction is going to shift to the left. Okay, it's going to reduce the total number of moles of gas. Okay, in this reaction, we just saw that if the pressure increases by the volume going down, the reaction is going to shift to the right, because here you've got two gas molecules, here you had four. Okay, some other ways that you can change the pressure without changing the volume. One of them is you can add more stuff to it. We already talked about that. That was the first thing we talked about. If you add more stuff, it's going to want to use that stuff up and cause a reaction to shift away from that. Okay, another way you can change the total pressure without making the volume bigger or smaller is you can throw in another gas or another substance that is not involved. Again, that's the key. It has to be a gas that is not directly involved. So say you have H2O gas and you throw in some H2. Well, H2 is not H2O. It's not directly involved. It has to be if it's the exact same gas, well, then you've got situation number one. But if you put any other gas in there that's not one of the gases that's involved in the reaction, then it's going to increase the pressure. Okay, argon is a very unreactive gas, often used to increase pressures. Okay, the important thing about that is when you throw in another gas that is, again, not involved in the reaction, it will not highlight that or do whatever. That's not the highlight, sorry. That will not cause a shift in the equilibrium. Only by increasing or decreasing the volume will the equilibrium shift. Okay, so if a gas is close but not exactly the same, then it's not involved in the reaction. It has to be one of the specific components of that reaction. Okay, now one of our final ones here is temperature. Now, when you add more stuff, if you add more H2 or N2 or NH3, that does not change the value of KEQ. It does cause a shift in the reaction, but it does not change the value of KEQ. When you change the pressure, that does cause a shift many times, but it does not change the value of KEQ. Okay? Changes in pressure or concentrations do not change the value of KEQ. However, when a temperature change occurs, so when the temperature changes in an equilibrium reaction, it almost always causes KEQ to change. Okay, this is the only time where you find KEQ will change, when the temperature changes. Okay, if the temperature is increased, remember that when we have an exothermic reaction, we know that heat is given off. So heat is like a product. Well, it's almost like you're adding, if you increase the temperature, you're increasing the heat that was a product. Well, just like how we saw with that first example, if you add more product, it's going to want to shift back to the left because you've added more product. It's going to want to use that up. So the equilibrium shifts in the direction that consumes the excess reactant or product, which is the heat. Okay, if it were an endothermic reaction, we know that heat would be a reactant because it's absorbing heat, it's using heat. If that's the case, then it's going to, if the temperature goes up, it's going to want to use up that heat that you've added, and it's going to cause the reaction to shift to the right. Okay, so in an endothermic reaction, we know that delta H is equal to a positive value. So they might not say endothermic, they might just give you a reaction and say delta H equals positive 72 kilojoules. You have to know that if that's the case, then you can simply take your reaction, say it's the N2 plus H2 makes the two NH3s. We got the 3 there. If it's an endothermic reaction, then you just throw heat right in there and treat it as if it were a reactant. So if the temperature goes up, that means the heat's going up. It's going to want to use that additional heat you've added. The reaction is going to shift to the right. In an endothermic reaction, if they lower the temperature on you, so the heat's going down, it's going to want to make more of that heat. So instead of the reaction proceeding to the right, it's going to want to proceed back to the left to produce more of that heat. Okay? So an increase in heat when it's endothermic causes it, like we just said, to shift to the right and vice versa. If it does shift to the right, remember that heat is not part of the KEQ equation. When you write your KEQ equation, heat is not in there. It's just the products over the reactants. Well, in this case, if it shifts to the right, NH3 goes up, these two both go down, and that definitely does cause a change in KEQ. KEQ does increase. Okay, in an endothermic reaction, as we know, heat is a product. So therefore, if you add more heat, again, it's going to want to shift it back to the left. When it shifts back to the left, the products go down, the reactants go up, and therefore you have a decrease in KEQ. So endothermic, remember, heat is a reactant. Exothermic, heat is a product. Heat is given off. Okay, and then our final one are catalysts. A catalyst, remember that when we looked at those energy diagrams where we saw something like this, where this would be the activation energy for that reaction from this point up. A catalyst is something that comes in and simply lowers the activation energy, and it causes the rate of the reaction to increase. Okay? A catalyst increases the rate, but the key, it does not change the composition of the equilibrium mixture. The equilibrium remains the same. the equilibrium constant remains the same, and therefore you do not get a shift. So with catalysts, you have no shift in your equation. Okay, it does not shift to the right, it does not shift to the left. The reaction remains the same. It just speeds it up. The rate increases, and that's it. But you have to remember that a catalyst causes no shift to occur in a chemical or in the KEQ equation. Okay, here's just a table kind of showing that, everything we just talked about. If the concentration increases, the reaction is going to shift to remove some of that. If the concentration decreases, it's going to produce more of that substance. So it's going to shift the reaction in that direction. Pressure, when you increase the total gas pressure by, again, decreasing the volume, the reaction is going to causes the total number of moles of gas to decrease. If the pressure, excuse me, I said this backwards. If the pressure increases, it's going to decrease the number of moles of gases. Don't make fun of me tomorrow in class about that. If you decrease the pressure, did I say this wrong? I did. I said it wrong again. Now, yeah, okay, you can make fun of me now. If you increase the total gas pressure, the volume does go down. Jeez, it's late at night. It's like 9 o'clock, all right, people? So the volume goes down, the pressure goes up. Yeah, there we go. I said it right the first time. So when you decrease the pressure by increasing the volume, it's going to increase the number of gas molecules. And then with temperature, again, when temperature goes up, if it's exothermic, then we know that heat is a product, so the reaction is going to want to go back to the left. If temperature goes up and it's endothermic, we know heat is a reactant. The reaction is going to want to go to the right. If temperature goes down, if it's exothermic, remember heat's a product, so it's going to want to make more of that heat, so the reaction is going to proceed to the right, and then vice versa, it's going to go to the left if it's endothermic. Just a nice table that kind of shows you. This is in your textbook. You can certainly look at that and see what's table 15.2 in your text is a good summary of all of those different laws. Okay, so let's say we've got a reaction at equilibrium. Oh, that's not in your notes. I'm sorry about that. Okay, in which direction will the equilibrium shift when each of the following changes is made? So if we add more N2O4, so this concentration or this pressure is going to increase, in which direction will the reaction shift? Okay, in that case, hopefully you said that it would shift to the right. It's going to want to use that additional N2O4 you've added, so therefore it is going to shift to the right. If you remove some of that nitrogen dioxide, it's going to want to make more of that, so it's also going to cause a shift to the right. If you increase the total pressure by adding some more nitrogen, well, this has nitrogen in it, and so does this, but it's not N2. N2, it would be a gas that is not involved in the reaction, so therefore it would increase the pressure, but it would not cause a shift in the reaction. So in that case, you would say that there is no shift. Okay, and then letter D, if you increase the volume, let me see if I can actually get this straight this time. If you increase the volume, what does that do to the pressure? You've got more space now, so now the pressure is going to go down. If the pressure goes down, the molecules now have more room to move around. It's going to want to shift in a direction that produces more gas molecules. So you're going to get a shift to the right. Okay, and then our final one, let's say delta H equals positive 65 kilojoules. That's a nice, I look like Bryson's handwriting, don't I? 65 kilojoules per mole. So we know that it's positive, so therefore using just that positive sign, the number doesn't matter at all, just the positive sign, we know that heat is going to be a reactant. Okay, If heat is a reactant and the temperature goes down, so our amount of heat goes down, the reaction is going to shift in that direction to make more of that heat. So we're going to say it shifts to the left. Okay, this was a question I believe on the 2006 AP Chemistry exam. Here we can see that U3O8 reacts with Cl2 to make UOCl2 an oxygen gas. And this was a question, this was on the free response, and you had to simply say whether it increased, decreased, or remained the same and justify your answer. It says after a certain period of time, 1 mole of oxygen gas is added to the mixture in the flask. So that doesn't affect this, doesn't affect this, it only affects this. So we're saying that more O2 is added. Does the mass of U3O8 in the flask increase, decrease, or remain the same? Well, using what we've just learned with the Chatelier's principle, we would say that an increase in oxygen will cause the reaction to shift in a direction that will use up that added component. So that will cause the reaction to shift to the left. A shift to the left will cause this to go down, but both of our products will go up. Some confusion might arise in that U3O8 is a solid and it is not part of the KEQ equation, which is true. However, that does not explain the fact that I'm not thinking of the right word here, but it still does affect the shift in the reaction. Even though the KEQ equation would only have O2 and UOCl2 and Cl2, a shift in a reaction still affects things that are not part of the KEQ equation. Okay, the book answer from this, they say that the mass of U3O8 solid will increase, and that was worth 1 point, because the reaction is at equilibrium. The addition of a product creates a stress on the product side. Okay, we added more O2, so that caused the stress on that side. The reaction will then proceed from right to left to reestablish equilibrium so that some of that additional O2 that's been added will be consumed, and so more U3O8 is produced. Okay, there's your wrapping it up there. Again, there's the catalyst. Do not cause a shift, and do not affect the magnitude. Temperature, remember, is the only thing that changes the value of KEQ. Changing the pressure, changing the amount of each reactant or product does not change the value of KEQ. Only temperature does. Okay, we'll take a look at these questions in class tomorrow. Thank you for listening.